Well, we are now in the wild, wacky, wonderful world of GPU programming, and you need a place to run this. Now, we have options. Flip is not one of them. Okay, does not have any GPUs on it. So Flip is not a good place to run GPU programming. We have another system that looks very much like Flip called Rabbit, which you're welcome to use because we bought it just for this class. But we also have a DGX supercomputer, some mini supercomputer that the College of Engineering has set aside a piece of for you in this class. And that's very cool. So let's talk about it. Okay, this is what it is. It is 6 of these boxes with the gold front. They're made by NVIDIA. Each box has 16 V100 NVIDIA GPU cards in it. So in here, there are 16 cards piled up. Anything in the NVIDIA line that ends in 100 like this is a GPU chip that doesn't have any graphics on it. No texture hardware, no rasterization hardware, all of that stuff. And in exchange for that, it can put more CUDA cores on it. And that's why you do it. You make a compute engine out of this. So there are 16 cards here and 16 cards there and 16 cards here, for a total of 96 cards in this whole system. These things are heavy. They actually had to be brought in with a little hand crane because they are just way heavy. But each one is front-ended by 2 Intel Xeons. Those are the submit machines, which we'll talk about. And each one of these V100s has about 5,000 CUDA cores and a fair number of tensor cores. And so that gives each one of these 16 boxes a total of over 80,000 CUDA cores, or the entire 6-box package, almost 500,000 CUDA cores. So yeah, there's some computing going on here. We're not going to use 500,000 CUDA cores. We're going to just grab one graphics card at a time. Okay, so yes, how do we do that? Oh yeah, Rabbit. I ran some Monte Carlo code on Rabbit, and then I ran it on the DGX. The DGX is about 10 times faster than Rabbit. We don't care because what you're going to find, if you haven't found it out already, is if you go to faster machines, then the shape of the curve stays pretty much the same. It's the value. And so, yeah, the shape of the curve, low for small data set sizes, come up, level off, shape of the curve's the same. Okay. And of course, you can use your own system if it's got a GPU in it to do the GPU projects, and you're going to get roughly the same shaped curve, just at a different performance point. Yeah, and here's Rabbit. Okay, so you want to use the DGX systems. How do you do that? We have 3 machines, submit-A, -B, and -C, that front end them. And so you are going to SSH to submit dash something .hpc, high performance computing, .engr.oregonstate.edu. When you get there, you're going to type this module load slurm. What is slurm? Slurm is a package that manages sort of multi-resources. Like, how do you get access to one of those? Slurm does that for us. So, but this is how you get your path set up in order to use Slurm. Okay, there are commands in Slurm, and if you've done this, those commands will now be in your path. If you say SQ, you can check and see what the queue is like, and this will be useful when you're running. And if you say sinfo, it'll show you a slightly different set of system information, but that's good to check. Okay, to submit a test job on the DGX system, you might do something like this. You make a script. So we're not just going to type at the command line. You do if you're on Rabbit, but here you're not. And so what you'll do is you'll type module load CUDA/version 10. We use version 10 because it runs on everything. CUDA, I think, is up to version 13, but some machines can't handle that. Version 10 runs everywhere, and we're not using the newer features anyway. We run the NVCC compiler, NVIDIA CUDA compiler. Looks just like G++, except your source is in a .cu file, and then we run it. So we say, bring in the CUDA path, compile it, run it. Yeah, ready to go. Now, again, you're on the submit machine. That's not where the graphics card is not there. It's kind of over there somewhere. So now you run a command called srun. You give it our class account number, our partition, and the name of the bash script that you typed in. We queues it, it's waiting to run, and then it'll print out what it got. Okay, that's it. Now, if you want to really, well, we're maintaining two partitions. One partition is called class GPU test. That's for your own debugging and testing. Another partition is called class GPU final. That's the one you want to use to take your final performance numbers. What's the difference? Class GPU test lets all of you run at the same time. Sure, you're competing with each other, but don't use this to get your performance numbers. They're not going to be representative, but you get to run right away. The GPU final partition only lets one person at a time run. And that way you've got dedicated resource, and that'll give you the best performance benchmark data you can get. So use GPU test when you're debugging and compiling. You'll get to run right away. Use GPU final when you're getting your final numbers. You may have to wait in line for that one. Okay, these are the things you put in the bash script. And this is now a whole lot more interesting options. Every line begins with #sbatch. Okay, technically that's a shell comment, the pound, but Slurm will interpret this as a batch command. Here's the job name, the account we're using, the partition we're using. Yeah, these mean other stuff. You can have your standard output directed to a file instead of printed at the console, your standard error directed to a file not printed at the console, and you can have it email you. You can have it email you when you are, well, when your job finally begins, when it ends, if it fails, and so on. And then the rest of the bash script is this. Okay, set the path for CUDA, compile your code, and run it. And then we say sbatch, and it spins it off in the background. And you can just concat the, well, I like to put my messages to the standard error file, but one of these is going to have your output in it. Okay, and so that's how you run GPU code on our DGX system. Now, when you say this is going to email this person with interesting information. And this is real handy. If you're in the take the final benchmark queue, you may have to wait a while to get to the front of that line because it's only letting one of you in at a time. This is a good thing to do. Just have it email you when the job's been run. But please spell your own email address correctly. Our IT people get really annoyed when they have to field all the bounced emails because you spelled your own email address wrong. Don't do that. And when I did it, spelling my email address correctly, this is some of the information I got. I got an email saying the job began. I got an email saying the job had ended. Very handy. Submitting a loop, same thing, really. We've got all these sbatch commands here, same as before, except now we will put a loop here in our bash script. And in our scripting notes, we talked about for loops in a bash script. So now we can change this for data set size. Here we can set it for block size and build it right into the code. So yeah, you put these commands as messages to Slurm and put this as things to run all in the same file, and then SBatch it. If you submit a job and you suddenly go, oh, I've made a mistake, and you don't want to leave it in the queue because then it's going to run for no good reason, there's an S cancel. You just have to know this number that came back when you submitted it. OpenCL, yeah, we're going to do this, except we're going to put in the whole CUDA path this time. But yeah, the OpenCL library is down under the CUDA path. All of this stays the same. And if you run print info on the DGX, here's what you get. Is it'll tell you what it's got. It'll say you've got 80 compute units. In NVIDIA terms, those are the streaming multiprocessors. Rabbit only has 15 of those, though. Yeah, this is kind of cool. But anyway, we are really lucky to have this DGX system here and to have the College of Engineering believe enough in you to let us all use it for this class. So definitely you want to take advantage of it. It is very cool and will give you really, really nice performance numbers.